So the first talk here is called Surprise Minimization Revision Operators. And it's about revision operators that minimize surprise. I'll just jump right in with a concrete-ish example. So, you know, the COP26 conference is going on as we speak. There's a lot of talk about global warming and what countries should do to prevent that. So I thought, you know, let's kick it off with an example in that area. So suppose I have some prior belief that of 5 major countries, so say Argentina, Brazil, Canada, Denmark, and the US, that of these 5 countries, either all of them, so either none of them or all but one will manage to halve their carbon emissions by 2030. So I made a little mistake here, either none of them, right? So this first disjunct here in phi is that none of them will meet their emission requirements by 2030, or all of them except the US. This is my prior belief, say, based on reading reports. But then I get some new information to the effect that maybe also, in addition, at most 3 of them will manage to meet their emission requirements. So A, B, and E. Now, this is a kind of contrived example, but I chose it such that it illustrates the main notions later on. So bear with me for a little while. But the idea is right now I have my prior belief, I have some new information, and I want to revise them. I want to find my revised belief. And I do this using the revision operator, the circle here. How am I supposed to do this? Well, very popular choice, a very standard choice is to use some kind of distance-based operator. For instance, the Dalal operator, which works, right, as we know, it looks at all the models of my prior belief, phi, and so chooses the models of mu, of the new information, that are closest to any model of phi, and then, right, it chooses those models of mu overall that minimize this overall distance to the models of my prior belief. It's called the Dalal operator. It's a classic operator. We know what axioms it satisfies, and so on, right? And it's based on distance. In this case, Hamming distance, which just counts the number of atoms that 2 interpretations differ on. And for this particular example, right, we can see how it works in a little table. So on the first row, we have the models of my prior belief. This is the empty set, so none of the countries will manage to achieve their emission targets, or all but one of them will. And then I have my new information here on the left, and I look at the Hamming distance between every model of the new information and to every model of my prior belief. And then the result of my revision is those models of mu here on the left that are at minimal distance, right? That you basically choose the ones that minimize the smallest number on each row. And the numbers, like I said a couple of times already, are distances. But the first issue I want to mention here is, what exactly do we mean when we talk about distances? So, right, what kind of intuitive content does this idea carry? And what I want to suggest is that this distance minimization perspective makes sense in right? And this epistemic perspective of revision, right? Where it makes sense to think of revision as you're learning about the world outside of you, right? So it's not just as, as Peter Gardenford says in Knowledge in Flux, it's just something that happens in your mind and the outside world never comes in play. There's no notion of truth. So on the contrary, I think it makes sense to think that there is that by revision, you learn something about an external reality. There is a notion, an underlying ground truth state, W star, which is the true state of the world somewhere out there. And the new information, mu, is a set of, or is a formula that encodes some kind of noisy observation of this underlying ground truth. And by getting this flux of observations, you kind of refine your prediction about what this underlying ground truth would be. And this is consistent with the epistemic perspective, very much in line with what Nina was talking about in the morning. And now the distance in this case is the divergence or the difference between what I think is the case initially, this is my prior belief, and what then might actually turn out to be the case, which is encoded by the new information mu. And so in short, it's the difference between, right, what I predict is the case and the reality out there. And this is, aptly described as a measure, I think, of surprise, right? So if I think the world is in a certain way, and then I get evidence to the effect that it's very different, then I would be quite surprised to learn that it's in this way rather than in another way based on my prior belief. And then revision then is used to resolve this tension, right? To help me choose between so when I get new information, to help me choose something that minimizes this amount of surprise that I feel. So for instance, in this example that we had in the beginning, right? If I think the world is will be either in one of these two states, right? Either empty set or ABCD. So if I get new information, then I will be very surprised if I'm in the state of empty set, I'll be very surprised that if ABCD turns out to be the case, much more surprised than if it turns out that I was actually correct and that empty set will be the case. Right? So surprise here it makes sense to minimize it in the sense that it's the thing, it allows you to resolve this tension between my predictions and reality. All right, but now, and in this respect, right, such a table of distances is kind of similar to what you see in decision theory, where the numbers represent something like utility. It's something that you want to maximize. Here, it's something. It's like the difference between, your mind and reality, and it's something that you want to minimize. And of course, right, there can be different ways of resolving this tension. So in particular, we have the tried and tested Dalal operator, which encodes a certain type of attitude, which is, you might describe it as a very optimistic attitude towards surprise, right? So it chooses those models of mu, of the new information, that have the chance of kind of confirming my beliefs in the best case scenario. So if I believe that empty set is the case, and it turns out that it actually is true, then I will be able to say, aha, see, I told you so. And it's the same for ABCD, right? In the case that so my initial belief, I'm kind of undecided about which of the possible worlds is going to be true on, but I think it's one of these two. And if it does turn out to be one of these two in the best case scenario, then I will be, right, this affords the least amount of surprise in the best scenario possible. And this is not an optimistic outlook because it only takes into consideration the best case that could occur. Alternatively, you could have a more pessimistic point of view, right, where you say, well, if I'm in this state, if the state of the world is empty set, and it turns out to be the case that A, B, C, D is true, then I will be very surprised, right? Then it turns out I was way off in my prediction. Whereas in the worst case, I will be very surprised. And if the true state of the world is A, B, C, D, and it turns out that it's the empty set, again, I will be super surprised. Whereas if it turns out to be this intermediate case where only 3 of them are true, then the amount of surprise is less, and it might make sense to say, well, I want to go for the safer option where the amount of surprise, where I minimize the maximum surprise that I get. And again, this is similar to what you do in decision theory, right? Where you for instance, sometimes you choose the outcomes that give you the best utility in the best case, or that give you the best utility in the worst case possible. So this is an operator that was introduced in a previous paper. And in this paper, I want to suggest another notion, another way in which you can do this, and it's what I call relative surprise. So this starts by first defining the notion of surprise based on notions of distance. And this is a notion that is based on Hamming distance, but also it takes into account the context of the new information that you get. And it's simply the relative surprise between 2 interpretations is the Hamming distance between them, from which we subtract the distance from V to mu. So this is the minimal distance from V to any model of mu. And then the corresponding revision operator is one that chooses the models of mu that minimize this maximum relative surprise operation. So we can see this on the particular example that we started with, right? We have the same prior and new information, except that in this case, the numbers, right, we normalize the distances by on every column separately. So by the distance from, for instance, the empty set to all the models here on the left. And in this case, right, because the new information is consistent with my prior belief, these quantities that we normalize by are 0, and things are similar to this max operator. But if we change the prior information a bit, right? So if we change the new information a bit, then things all of a sudden look different. So the distance from empty sets to these 2 interpretations is 3 now, and now the distances get normalized by 3 here, and ABCD turns out to be the world that is chosen. And why does this make sense? Well, again, it's this idea of trying to negotiate my attitude towards surprise. So in the top example, if I'm actually in world A, in the empty set, then I would be, both of the worlds ABCD and ABE are surprising, but ABCD is not that much more surprising than ABE. Whereas in the latter case, right, it's a kind of how much more surprising would a world be relative to the other one. So here ABCD is not much more surprising than AB, but both of them are quite more surprising than empty set. Whereas here, right, the difference between them is not as significant as to recommend one over the other. So what are the postulates, right, that describe these operators, right? We have 3 now, the relative surprise one and the min and max one, the Dalal and the max one. Well, we know that the Dalal operator satisfies postulates 1 to 6, right? These are the standard Katsuno-Mendelssohn postulates. we know that Dalal satisfies it. It's not the only operator that satisfies them, but we know that it satisfies them. The max operator satisfies all of the standard Katsuno-Mendelssohn ones except R2. So R2 says that if new information consistent with prior information, then the result is the conjunction of the two. The max one doesn't satisfy this, but it does satisfy two different postulates. So these postulates contain this bar phi, which is the dual of phi. So the dual of phi replaces every literal in phi with its negation, and it kind of says try to avoid the models of this dual thing. So the models of this dual thing are things that I really don't want to believe unless strictly necessary, unless I don't have any other option. So these are kind of duals to this R2, which this max operator satisfies. And if you look at the new relative surprise operator, what it does, the postulates that it does satisfy are so even less of the 6 classic Katsuno-Mendelssohn ones. So it doesn't satisfy 2, and it also doesn't satisfy 5 and 6. So these are the ones with where you add new information about which to revise. And it also doesn't satisfy the other 2 that the max operator satisfies. So a short note here is that if the original formula is complete, if phi is complete, that is to say it has only one model, then all operators give the same results. But if it's not, then we have different things. And to see, for instance, why the max operator doesn't satisfy 5 and 6, you look at how it orders, how it creates these orders, these rankings on possible worlds. And right, so 5 and 6 basically in the proof, they tell you that this ranking on possible worlds depends on nothing except phi. Whereas here you can see that the ranking between ABCD and ABE in one case, right, and so they're both part of the new information, but depending on the context, which is this empty set, right, the order between them changes from one case to another. So in the first one on the top, ABE turns out to be better than ABCD because, right, the relative surprise it gives you is less, is smaller. The relative maximum surprise, right, is smaller. Whereas here, the order between them, all of a sudden ABCD becomes more appealing because, right, the relative surprise in the worst case is smaller than the relative surprise in the worst case of ABE. Right, so the order between them swaps depending on mu. And this is something that you don't see in standard revision operators, but you do see with this new type of operator. So the question now is, of course, well, if it doesn't satisfy these standard axioms, what axioms does this operator satisfy? And the paper then answers this question. And it answers it in a kind of interesting way, I believe. Right. So for this, we just first have to look at a couple of new notions. So we need a notion of renaming atoms. So renaming is just a permutation on a set of atoms. So if you look here on the right, you have a formula A and not C, and then you have a permutation that sends A to B, B to C, and C to A. And then the permutation applied to the formula phi is just phi is just the permutation, is just the formula that you get by applying the renaming to the individual atoms. And then an interesting thing that is quite useful then is that this operation carries on to the models. So the models of the renamed formula are the renamed models of the original formula. So it's just you're changing the labels of the atoms. Then you have another operation, which is a flipping function. So a flipping function basically turns on or off certain atoms. So it replaces atoms with their negation when they occur. So for instance, in this formula, if you flip B and C, then, well, you don't touch A. B doesn't appear anywhere, but C appears in A and it gets replaced with its negation. And on the semantic side, what flipping does is it kind of turns on and off the corresponding atoms. So when you flip B and C, right, if you look at this interpretation A, then B and C were originally off. Then by flipping, you turn them on. And it's the same here. You turn B off and you turn A on, and you turn C on to go from AB to AC. And the result is the models of the flipped formula are the models I get by taking the symmetric difference in the models of the original. So this is also a kind of intuitive operation, I think, where you flip things back and forth. Then something less intuitive is something called the best of best formula. So this uses this epsilon, which is a formula, the null formula, where everything is set to false. Oops. And what it does is it says when you get new information mu, AC and BC, you flip it according to every model of phi, right? So you have different copies of mu flipped according to every model of phi, right? So here you get two sets, and then you revise the empty formula by all of these models, by the union of these models. And it's not so clear why you want to do this, but I'm going to explain it now, right? So we have on the one hand a bunch of new axioms. One is a neutrality axiom that says prescribes invariance under renamings, right? So if you a revision operators should be invariant under renaming. Then you have a flipping axiom, which again it says the revision should be invariant under any flips. Then you have an addition axiom, which says that if you have a complete formula and then you revise by a formula that has two models, W1 and W2. So this basically says if you have a choice between these two models, W1 and W2, and you choose W1, then if you take W2 and you just add some new atoms to it, then W2, just by adding new axioms, it doesn't make W2 better. It doesn't make it chosen eventually. And then you have this best of best formula, this best of best axiom, which uses the best of best formula to put a constraint on the revision result. And then the nice thing about this is that you get to characterize the Dalal operator. So this is going beyond the standard Cassino-Mendelssohn axioms. These are stronger axioms that actually manage to characterize the Dalal operator. And the way this is done is by using these intuitive operations of flips and renamings. So the argument in very brief terms goes like this. If you're in the situation where your prior belief is empty set and you have to revise by A and B, then Dalal, right, using the distance argument with the numbers, will tell you have to choose both A and B. You can make a difference between them. And you can simulate this by renamings, right? So because the empty set is invariant on renamings, then if you were to choose A over B, then you can apply a renaming argument then to conclude that you should also choose B over A, which would be a contradiction. So you have to, because of the renaming, you have to treat A and B equally in this case, and you have to choose them both. So this is consistent with what Dalal would do. Then by this addition axiom, you can also ensure that A gets chosen over AB here, right? Intuitively, if it wasn't, if AB was chosen over A, then you could add new atoms to A, and until you have it be the same cardinality with AB, and then you apply a renaming argument to show that this modified version of A would have to be chosen. So again, a contradiction. Then, right? So far we had arguments that used the empty set as a starting point. Then you can show that for if you have any one interpretation as a starting point, as your prior belief, you can use flipping to show that, right, to simulate this Dalal distance thing, right? So if you start from, for instance, AB, then you just flip every atom in the prior information to get to this point where the empty set is, right? You reduce it to the previous case. Flipping preserves Hamming distance. So now you can apply the previous argument to show that B should be selected here over BC. And now you've basically shown that, using these three actions, neutrality, flipping, and addition, you can simulate Dalal on when your prior belief is complete. What about the case when the prior belief contains multiple models? Well, this is a little trickier, and this is where this best of best formula comes in. And the way it works is, right, say you have a prior belief that has models A and B, you revise by AC and ABC. So what you do is, first you flip all the models first you flip the first model of mu, and you get C and BC. Then you flip the models of mu according to B, and you get two new models. So now you're revising, right? You have you have different copies of mu, all flipped according to the models of phi. And you the idea is to bring them all to a common denominator, right? To create this choice situation where the model doing the choice is the empty set, and you do this via flipped. And now you look at what the empty set would choose in this situation, and it would be C, right? Based on the on the previous argument. Now, C corresponds to a model of mu, which you get by flipping back, right? By reversing this flipping operation, and then taking the intersection with mu's, right? So it's those models of mu that end up being chosen by the empty set in this kind of flipped, in the situation where everything is reduced to this common denominator. So in this case, you're able to simulate this idea that Dalal chooses the best models of mu, right, according to, in every, right, the best models of mu according to every model of phi. So this is very nice, right? It gives you a characterization of the Dalal operator. Then you can do something similar for the max operator. So for the max operator, you look at you don't look at what the, okay, that's good, yeah. You want to look at a different situation. So it's not what the empty set chooses, but what a different formula. So what's called here the where is it? It's this alpha. This is the full formula. It's a formula that has where every atom is set to true. So that is to say, it's a formula that where all the atoms that has as a set of model all the atoms, right? And this, you want to see what models would this, what models of mu would this formula choose, right? So this intuitively says, pick the worst, see what the worst models of mu are, right? And they are the models that are at the smallest distance to this full formula. And now, using the same kind of sequence and flips of flips and renamings, you can show that, and a special axiom that here is called best of worst, right? You can characterize the max operator in this way. So the same ideas that gave you the Dalal operator, right? Using this neutrality and addition and flips, and this particular type of axiom that tells you what you're supposed to do when you have multiple choice situations, right? Corresponding to the multiple models of phi. Yeah, this turns out to characterize the max operator as well. And then last but not least, right? So this relative surprise max operator that was introduced here, maybe unsurprisingly, the same ideas turn out to characterize it. But here, what you have to do is, so again, it's a little tricky because the distances in the table, they kind of depend on what your new information is. But what you can do is you can recast the revision problem here as a revision problem according to this max operator from the previous slide, but on a modified prior belief. So instead of having phi, instead of doing revision, right, instead of doing relative surprise on phi, you do max revision on phi star, where phi star is defined such that it has these models B star, V1 star to Vn. And these V1 stars to Vn, what they do is you kind of pad them with new atoms such that intuitively you add M1 plus M2. So M1 and M2 are the numbers that are subtracted here on every column. And you want to kind of bring this to a common denominator, to a situation where you can apply the max operator. So you pad it with new you pad V1 and V2 with new atoms, which is this M1 and M2 sets, and they create a situation where you can apply basically the max operator. And this we know how to deal with from the previous slide. And the intuition here is encoded in a particular axiom that uses the same kind of flipping arguments, except that now you use it on the V star on the V star models rather than the V ones. Okay, and then in this way you can characterize this operator as well. So to wrap up, right, in the paper, what you get to see is this relative surprise operator based on Hamming, this notion of relative surprise, which is in turn based on Hamming distance, and minimizing the maximum relative surprise. And this is, I think, interesting because it also introduces a notion of context, which I think you don't see so much in revision, where this ranking on possible worlds depends not just on the prior belief phi, but also on certain things, right, in the environment. In this case, on your new information mu. But of course, it could be other things like, you know, your peers or things like that. Yeah, and then we characterize this. I characterize this operator using a set of intuitive operations. I think they're quite intuitive, right? Renamings, flips. These are things that you see in social choice, and they're quite useful. And I think they're quite powerful because they turn out to be versatile. That enough that, you know, the same kind of ideas with slight tweaks in these best of best and best of worst axioms, but right, the same core of ideas also give you the Dalal and the max operator. So you can kind of see them as general principles that underlie, right, that are useful in talking about all these operators. Yeah, so that's all I have to say. Thank you.